Okay, today we're going to be looking at three things. So we're going to be talking about variables. This is the first major topic that we will be looking at. In order to understand variables, we do need to back up a bit and talk about computers. So I will give you kind of a very broad overview or understanding of computers, enough so that we can define what a variable is, and we'll look at how do I create a variable, how do I use a variable, and then we'll look at different types of variables. Okay, so here is my very rough sketch of a computer. And the story begins down here at the bottom. So this is the hardware layer. Hardware refers to any component of a computer that you can touch, that's tangible. And the hardware is composed of a lot of different components, but three of the most important components are the hard drive, random access memory, otherwise known as RAM, and your CPU. Okay, so starting with the hard drive, so if you were to open up your hard drive, you would see inside that there's a platter, kind of looks like a CD, and there is a little arm here that has a little head. And basically what happens is all of your data, your music, your photos, your essays, your homework assignments are stored permanently on your hard drive as a sequence of zeros and ones. And the way that those zeros and ones are encoded is using magnetization. So the head, this little arm, has a little magnetic head, and it is capable of magnetizing or demagnetizing these cells that are on the platter. And so let's say your essay, for example, it's a stream of 10,000 zeros and ones, and the magnetic head goes around and it starts magnetizing, magnetizing, demagnetizing, demagnetizing, magnetizing, right? 1 1 0 0 1 0 0 1 1 1 1 0 0, right? And that's your essay being stored, encoded in binary. So that's your hard drive. It's storage. It stores everything, homework assignments, photos, everything. It stores them in binary using this magnetization scheme. And it's permanent storage. So if you were to turn off the power to your computer, when you turned it back on, you would find that your data is still safely stored on the hard drive. Contrast that with RAM, random access memory. This is also storage. However, it is much smaller than your hard drive, so it's not capable of storing as much. And also it is temporary. So if you turn off the power to your computer and then you turn your computer back on, RAM has been wiped clean. So you may wonder, if they're both storage, but the hard drive is both bigger and permanent, then what's the purpose of RAM? It seems inferior. Well, the one benefit of RAM over the hard drive is that RAM is much faster. It's got a better speed. So the hard drive is mechanical, meaning that platter is mechanically spinning, and this arm here is moving back and forth mechanically, whereas the rest of the components in your computer are digital. And digital is much, 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 much faster than mechanical. So whereas RAM is smaller and temporary, it is incredibly, incredibly fast. Okay, last but not least is you have the CPU. The CPU is what makes your computer a computer. It's like the brain of your computer. It's a chip, and on the chip it has logic so that it can perform very basic actions like addition, division. It can check if something is true or false. It can move something. It can fetch something, right? So very basic operations, but it can use those basic operations to execute more complicated actions, such as launching iTunes and playing a song. Okay, so the CPU is what makes your computer a computer. It is the brain of your computer. So the way that these components work together is that when you open up, for example, Microsoft Word, and you load the essay that you're working on, that lives on the hard drive. Microsoft Word, the program, the code for that program lives on the hard drive. Also, your essay lives on the hard drive. So when you launch it, your hard drive spins up and it locates Microsoft Word in your essay and it loads it into RAM. From that point on, as you are typing and doing stuff, the CPU and RAM are communicating with each other, but we don't have to access the hard drive anymore. That means that the CPU and random access can work at digital speeds and they can go really fast. In fact, if you were to open up a computer, the CPU and the RAM are often located quite close to each other just to get as much speed advantage as you can. So the CPU and the random access memory, they're working back and forth, back and forth, back and forth. And then when you hit save and you want to permanently save your essay, that's when your essay, the updated version from RAM, is loaded back to the hard drive and it's stored permanently. Okay, so that's kind of the flow of how these three components work together. Sitting on top of that is the software layer. Software refers to any piece of your computer that you can't touch. It's the intangible part. And probably the most important software program is your operating system. Your operating system is this massive, invisible program that you probably take for granted unless it crashes or annoys you. So it is the first program that is loaded when you turn your computer on. It is always running. It's what's responsible for displaying your desktop. It takes care of all of your folders and your file system. When you search for something on your computer, it's the operating system that you're interacting with. It's this massive program that makes it easier for you, the novice user, to actually use this very powerful machinery. Without the operating system, you would have to learn how to communicate directly with the hardware. No one wants to do that. Okay, so it's what basically makes personal computers personally usable. Sitting on top of that is the software that you are aware of: Firefox, Internet Explorer, Safari, Word, iTunes, BlueJ. All of those are programs. They are also software. When you open one, so for example, if you open, let's say, iTunes, because you want to play some music, iTunes communicates with your operating system and your operating system communicates with your hardware. So the operating system also acts as this middle layer between the software world and the hardware world. So iTunes would say, hey, the user wants to play this song, and it tells that to the operating system. The operating system gets the hardware to load the song into RAM. Then the hardware communicates back to your operating system saying the song is loaded. Then the operating system alerts iTunes and your song begins playing. Okay, so the operating system is this middleman. So this is a very high level view of your computer. And we're going to focus today on random access memory. So we're going to zoom in and really look at what is random access memory, or in particular, what is the format of random access memory? And it's a storage mechanism. It's used to store things. And so we're going to see how storage for us is represented as variables. Okay. Okay, so on the left here is a picture of RAM. This is, I tried my best here to kind of replicate that picture, but here's an actual picture of what RAM is. If you were to open up really a desktop computer, you would see these sticks. They're green, they're little sticks. You click them into your motherboard, and the more sticks you have, the more memory you have. So you can actually add more memory just by putting in more sticks. Okay, if we were to take a ride on the Magic School Bus and we were to zoom in and get, infinitesimally small so we could go inside of RAM and look at it, okay, this is what we would see. Okay, so this is us zooming in. We would see that RAM is nothing more than a series of empty storage locations. Okay, so each of these is a storage location. Dot, dot, dot. Okay. Each of these storage locations is capable of storing a single unit of data. Each of them has a memory address. You'll see that I'm counting by 8. Okay, that's because the unit tends to be a multiple of 8. 8 bits is a byte. So each of these empty storage locations has a memory address in the same way that houses have mailing addresses. We give houses mailing addresses because we want to be able to refer to them and we want to be able to send things to them. In the same way, memory locations have addresses so that we can refer to them, we can store things in them, we can access them, so on and so forth. Okay, that's really all random access memory is. It's just an array of places that you can store stuff. the end. Okay, so when we talk about variables in Java or variables in computer science, for us, this is the definition that we're going to work with, and it's the same one that's in your textbook. So what is a variable? A variable is a memory location that stores a value of a particular type. A variable is a memory location that stores a value of a particular type. Okay, so a few important pieces of that definition. A variable is a memory location. So we're going to learn in Java, how do I create a variable? What is the syntax? What's the code to create it? And we'll see that when you create a variable in Java, truly, it is a memory location. Okay? This memory location stores a value, and that value has a particular type. And that is maybe the most important part of this definition. I said this in the last video that in computer science, the type of an object is incredibly important. And so here, when you create a variable, it is a memory location. I'm storing a value in the memory location, but I have to specify the type of that value. Is it an integer? Is it a floating point? Is it true or false? What are you storing? Okay, so how do we actually, in terms of Java and code, how would we create one of these variables? Okay, so here I'm going to write an example of declaring and initializing a variable. So int, which is short for integer, temp equals 45. So here, this is my variable type. So when you declare or create a variable, you need to tell the computer what the type of the variable is. In other words, what's the type of the value that you'll be storing. By specifying int, I'm saying that this variable will only ever store integers. And if I attempt to store anything else in this variable, the computer or the compiler will throw an error. Next is the variable name. Again, this is up to you to decide. It should be lowercase, only classes are uppercase, and it should be relevant. The end. This is the assignment operator. We use this operator when we want to store a value into a memory location. Last but not least, this is an initial value. So int temp equals 45 semicolon. So in the computer behind the scenes, when this line of code is executed, the effect of that in terms of RAM is as follows. So on the left-hand side of the equals, I have int temp. What that's doing is it's declaring a new variable, and the name is temp. So the computer will look through RAM, and it will find an empty spot, and it will associate with that spot the variable name. So this is now associated with temp. On the right-hand side, then I have an initialization, and I'm giving it an initial value of 45. And so that is what gets stored in memory. From this point on in my program, every time I use the variable name temp, it's really a placeholder for the value 45. Just like a variable in mathematics, it's kind of nice having a variable whose value we can update and change so that we don't always have to work with hard-coded numbers. Okay, let's do some more examples. So maybe I'd say int age equals, and let's do some math to compute my fictional age. So this year is 2020 minus 1994, the year I was born. So here, when this line of code is executed, on the left-hand side, again, we have a declaration. So the computer finds an empty memory location, associates the name age with it. On the right-hand side, we have an initial value, but the computer has to resolve that expression first. So it performs the subtraction, 2020 minus 1994, 26, and that's the value that gets stored in here. One last example, we could do int mom's age equals age plus 30. So again, when this is executed by the computer, on the left-hand side, we're declaring a variable. So we associate an empty memory location with the variable name mom's age. And then on the right-hand side, again, for our initial value, it's an actual expression. The computer has to evaluate this expression. So it first looks up what value is stored in age, which is 26. We add 30 to that to get 56, and that's the value that gets stored in mom's age. Really quickly, I do want to note that you can declare a variable without giving it an initial value, and then later on assign it a value. For example, I could say int temp. So we could have said int temp. Notice here, it will find, the computer will find an empty memory location and assign it the name temp, but the value inside is left unspecified, it's undefined. Usually this isn't a good idea because if you forget to assign temp a meaningful value and you try to use it in some sort of computation, the value it's storing is undefined, it's unspecified, and wonky things can happen. In fact, usually the compiler will catch that and say, hey, you're trying to do arithmetic with something that you didn't actually give a value to. So, okay, so we could give it a value. So then we could say temp equals 45. And it's important to note that this second line here, let's do that in red. This is an assignment. It's an assignment statement. It is not an initialization. Initialization, and that doesn't even look. Okay, it is not an initialization. Although functionally, these two code examples are doing the same thing, like the net effect is the same. I have a variable and it stores the value 45. Here I'm both declaring and initializing at the same time. Here I'm declaring, leaving the initial value undefined, and then I'm doing an assignment. And those are slightly different, although the net effect is the same. Okay, so this is what a variable is. So let's talk now about what do we do with variables. Oh, I need another sheet of paper. Okay. Hopefully it's clear to you the usefulness of variables. I think if you've taken a math class and if you've ever taken like pre-algebra or algebra where you start working with variables, the usefulness is that I can have a variable, I can do things with it, I can symbolically manipulate it, and the value of the variable can change, but my manipulations don't need to change. Okay, so I can compute this whole formula, and then I can say, okay, let's have the variable be 5, right? And then I can run it through that formula, and then I can say, okay, now I want to see what the value would be if the variable was 10, right? And so my manipulation, my code doesn't have to change. I can just change the value of the variable. So hopefully at a high level philosophically, you have a sense of why variables are useful. We're going to talk here more practically about what do I do with them. So once I create a variable in Java, what do I do with it? Okay, so uses of variables. The first use, kind of regardless of the type of your variable, the first thing you can always do is print. Okay, so you can always, regardless of the type of your variable, print it. So for example, we could say system dot out dot print ln. Today's temp is So here I have a print statement. When the computer executes this line of code, it recognizes it's a call to the println method, looks good. And then when it looks at the input, in other words, it looks at what we're passing between the parentheses, we have a string literal and a variable. So the first thing it has to do is it has to go to memory, look up the value of this variable. Okay, that gives it the number 45. And then just like we talked about last time, it takes 45, turns it into the string literal 45, and then concatenates these two strings together. So we see printed, today's temp is 45. Okay, so regardless of the type of your variable, you can almost always print it. In fact, I think you can always print it. Okay, the other uses of a variable depend upon the type. That's why the type is so important. Depending upon the type of your variable, you may be able to apply different operators and perform different functions with them. Okay, so when you ask me what do we do with variables, tell me its type, and then I can tell you what you can do with it. Printing, you can do with any variable of any type. We are going to start focusing really on variables of numeric type. And so these next two uses are things that you can do when you have a variable of numeric type. Okay, so the second use of a variable, okay, you can use it as a value on the right-hand side of the equals, of the assignment operator, okay? So we already saw an example of this. Previously, I had int age equals 2020 minus 1994, okay? And then I said int mom's age equals age plus 30. Here's an example where I'm using a variable on the right-hand side of an equals, on the right-hand side of the assignment operator. I'm using it as a value, right? It stores a value, and so I can use it in place of a value. So when the computer looks at this line of code again, on the right-hand side, age is standing in for the number 26. Okay, so that's one use. You can use it on the right-hand side of an equals as if it was a number, and you can multiply, add, subtract, so on and so forth. Last but not least, you can use it as a storage location on the left-hand side of the equals. Okay, here's an example. Now, this is an interesting example for a number of reasons, and so let's walk through them. So here's a piece of code. Assuming that I've already written int age equals 2020 minus 1994, and int mom's age equals age plus 30. And then I wrote age equals age plus 1. So the first thing I want to note is that age is being used on both the left and the right-hand side of the assignment operator. For a human being, this is sometimes makes us a little bit uncomfortable. We feel like there's a little bit of ambiguity going on, not really sure how to evaluate this. Thankfully, computers do one thing at a time and they do it sequentially, so they're not really fazed by something like this. So when the computer executes this line of code, it has to first evaluate the right-hand side. So it will look up in memory what is being stored in the variable age. It finds the number 26. It adds 1 to that to get 27, and then it takes that answer and it stores it back in the variable age. Okay, so after this operation, after this line of code is executed, the variable now stores the value 27. So because the computer isn't a human, it doesn't just mystically evaluate things like we do in our brain, it has to break everything down into discrete steps so it doesn't ever run into a problem with having age on both sides. It evaluates the right-hand side, stores it in the left-hand side. 2, this is an example of using a variable as a storage location. Anytime you have a variable on the left-hand side of an equals, implicitly what you're saying is store it, not implicitly, explicitly what you're saying is store whatever the solution is, whatever the value, store it into this variable that is the memory location. And then the third observation I want to make about this example, notice that the only time I have to tell the computer the type of the variable age is right here. When I declare the variable, that's the only time I need to specify its type. So here, when I declare age, right, I'm indicating it is an integer variable. From that point on, though, I am able to use age, and I never have to re-specify its type. Okay, so you declare the type once and only once at the beginning. From that point on, you can use the variable name and you don't have to re-specify the type. You can just use the variable name. Okay, so those are some uses of variables. This first one is a global use, like you can print any variable. These last two are really specific to variables of numeric type, like integer. Okay, last but not least, let's talk about different types of variables. So far, we've seen the integer type, and that's all we've seen. There are 8 what are known as primitive types in Java. These are types for your variables that are built into Java, so you can use them without having to do anything fancy. And so those are why they're called the primitive types. Think of them as the basic types. Okay, so here are the 8 primitive types, and then we'll look at some quick code using these types. The first one is byte. Okay, this is a type whose value is any integer in the range -127 to positive, to positive 127. So if you have a variable and you know that its value will never be outside of this range, then you can use the byte type. For example, age is a perfect example. Like, it's rare to meet someone, okay, no one is negative in age, and it is almost impossible in today's modern age to be older than 127. So if you had a variable representing age, byte would be a really good type for your variable. And we'll talk a little bit more about that later. Okay, the next type is called short. This is also an integer type. This has a range from -32,000 to positive 32,000. Next is int, which is what we've already seen an example of. This is also an integer type. This can store any integer between -2 billion and positive 2 billion. Pretty big. If that is not big enough for you, there is actually a type called long. This is also an integer type, and it's really big, meaning the range of values that it can store is just really big. Nothing more to say. Okay. Next, maybe you need floating points, meaning you need a number that has a decimal place and numbers after the decimal place. So the first is called float. This is a floating point type. And its range is -3.4 times 10 to the 38th to positive 3.4 times 10 to the 38th. If that is not big enough for you, there's a type called double. It is also floating point, and it has a really big range. Then these last two types are not numerical types. So these will be our first example of variables that you can create whose type is not numerical. So the first is char, also pronounced car. I say char, which is probably incorrect. It should be car for character. Whatever, I don't know. I say char, some people say car, the end. Okay, this type, right, stores values that are characters. By which I mean any single symbol that you can type on your keyboard. These characters are represented. So to distinguish between a character, which is a single character, a single symbol, and a string literal, which is a sequence of characters, we use single quotes for the characters, double quotes for the string literal. Okay, so an example of a type of character that you could store in a variable of type char, capital A. Other examples, lowercase b. Perhaps you want to store a semicolon. These are all characters. They are one single character. We use single quotes instead of double quotes. They're not string literals. They truly are characters. Last but not least is the type Boolean. Okay, this stores truth values. And a variable of type Boolean can have one of only two values. It is either storing the value true or it is storing the value false. Okay, using the exact same syntax that we did with an int. Okay, so here, we can create now variables of any of these 8 types. We will be focusing on integer types and double types. If you were taking this class maybe 20 years ago, you would have been much more parsimonious in your use of memory. Memory now, it's pretty cheap. Your cell phone has more memory than a computer 20 years ago would have had. So nowadays, for many applications, we don't have to think so much about conserving memory. So even if I had a variable age, and I know it's never going to take a value larger than 127, so I could use a byte, you almost never would. You would just use an integer, and it's kind of wasteful, but it is what it is. Similar with double. If you had a floating point variable, and you know that its value is never really going to be that big, you could use a float. You're just going to use a double though. Okay, so ints and doubles are going to be the two numerical types that we almost exclusively use. It's good to know about the other ones if you do need to be more parsimonious and conserve memory. But in today's day and age, memory is so cheap, we kind of have bad programming habits. It is what it is. Okay, so we're going to use ints and doubles. Okay, last but not least, I want to look at some examples of creating variables of each of these types. And then I'm not really doing anything but printing with them. I think in the next lecture and the next lectures, we'll start actually doing math and using these variables for something more interesting. But right now, it's basically just printing. Okay, so here I am declaring one variable for each of the 8 primitive types. So I have my age, salary, 30,000, circle width, 200, population. Right now, the Earth's about 7 billion, so that's what this number is, 7 billion people on the planet Earth. Size, 40.2, radius, letter grade. So here's an example of a character, not a string literal. Notice the single quotes, and game over equals false. You will notice that anytime you have a number, like a literal actual number, and it is a long, meaning it is larger than 2 billion, you need to put an L at the end to tell the computer Please interpret this number not as an integer, but as a long. Similarly, if you have a floating point number, you put an F at the end to say, please interpret this number, not this variable, but this number as a float, not a double. I could talk longer about why it is that way, but I'm not going to. The end, okay. Okay, so here I'm printing each of those variables, not the coolest application, but just so you can see them being used. Then I am assigning, I'm using the assignment operator, and I'm assigning new values to each of these variables. Again, this looks very similar to the int examples that we were doing. So here I'm just updating age to 110, salary, you got a raise, circle with population, 1 person was born, so on and so forth. Okay, and then I'm reprinting them. So we can compile this and then run it. And there we go. So we see all of these printed out. Again, when the computer executes the print statements, it goes to the variable, looks at the value, and that's what gets printed to the screen. Okay. Okay, so that's basically it. A quick recap. So here's how a computer works. We're looking at random access memory, which is a storage mechanism. If we were to zoom in, we would see that it's nothing more than a sequence or an array of empty memory slots. Each slot has a memory address. When you create a variable, you're associating a name with one of those memory locations. That memory location stores a value, which you specify, and it's a value of a particular type. Here's an example of how you can declare and initialize a variable in one line of code, or you could declare but not initialize, and then later on assign the variable. What do you do with the variable once you have it? Printing. You can always print, and for numerical types, you can use it on the right-hand side in place of a value, as we see happening here with age. You could use it on the left-hand side as a memory location, as we see happening here. Or you could use it on the right and left-hand side. The computer does not get confused. And then again, you only specify the type when you declare the variable. From that point on in your code, you can use the variable without needing to specify the type. Last but not least, in addition to integer, there's actually other types, byte, short, so on and so forth. Each of these types has its own range, its own set of values that it can store. Even though we should, and maybe we could and should be parsimonious with our use of memory, we're just going to use int and double. It's kind of good enough for all of your basic needs. And I think that is about it.